So thank you, Professor, for the introduction and for the invitation to this online conference and faculty development program. Yeah, so my talk will be mostly for the students who wants to work on quantum information. So who like knows some of the basic things and then wants to work on this topic, right? So I will basically explain a few things in details, and then I will discuss a couple of more things, right, on quantum communication. So quantum communication. So there are many aspects of it. So one is like the quantum cryptography, and that's of course very important. But it's not that there's only quantum cryptography in quantum communication. So there are ways where we see that sending a quantum bits is more powerful than sending a classical bits, right? And or in general, sending a d-dimensional classical system, it's not powerful as sending a d-dimensional quantum system. So there are many things that you can do with the like quantum correlations and sending quantum systems in communication, and then we want to explore those things today. Okay, so I will just start with the basic postulates or the basic descriptions of the physical processes in quantum theory. So any preparation we can describe by a normalized vector that belongs to some Hilbert space. And then any measurements that we can perform on the quantum systems is described by a set of projectors. So if we have, let's say, a measurements that has like d possible outcome, and so there are d possible projectors such that there's some identity. This is also equivalent of saying that there's a Hermitian operator that has like d different eigenvalues and correspond to the different projectors. And then if I prepare a state psi, and then if I measure the particular measurement that is described by this set of projectors, then the probability of getting outcome A is given by the Bond rule. And then if I get an outcome A, then the state collapse according to the collapse rule. And then the time evolution of a quantum state is described by a unitary operator. So and then the state will be, if the input state is psi, then the output state after the time evolution will be like u psi. And then the last postulate tells about the composite system. So if we have a composite system that has like two subsystems, then the entire system is associated with the tensor product of the Hilbert space of the subsystems, and then we can also consider the measurements, time evolution, everything on the composite, on the tensor product of the Hilbert space, right? Yeah, so for example, if I want to measure something on the system A and some other observables on system B, then each of the observables is described by some set of projectors, and then the probability of getting outcome A on system A and B on system B would be something like this, right? And then we can realize all possible quantum states, measurements, time evolutions, and everything within some physical systems. And when we talk about quantum communication, the most relevant physical system is photon. And mostly we use the polarization degrees of freedom to realize like all the quantum states, measurements, and everything, right? So for example, if I want to, let's say, prepare a state plus, then what we can do, we can take a source of photons. This is a single photon source, let's say, and then we can first place a linear polarizer. So it's like it's a polarizer such that the state is like comes out to be 0, and then you can just put a, let's say, halfway plate with angle pi by 8, then the state of the polarization of this photon will be plus, right? So like this, we can realize any quantum states, and similarly, we can also realize sort of quantum measurements. For example, we are talking about the polarizing degrees of freedom. So we have to measure certain observables. Let's say we want to measure like sigma z, right? So it's like in the 0, 1 basis, right? We want to measure this. That what we can do is like we can just place a polarizing beam splitter, and then we can place 2 detectors, and then it's a photon. The state of the photon, I mean, the polarizing degrees of photon is like some state psi, and this would corresponds to, yeah, like this is like if the photon is detected here, then that means the outcome corresponds to this has occurred. If the photon is detected here, then the outcome corresponds to this vector, right? So this is the way we can realize different measurements. We can, if you want to measure in other bases, then you can use like the half-wave plates and quarter half-wave plates. Okay, and the time evolutions we can also realize it by optical elements like half-wave plates, quarter half-wave plates, and phase retarder, and everything is there. So if you want to realize certain gets, we can realize it by appropriately placing those optical elements. And then you can also generate entangled photons using the parametric down conversion, right, in the optics. And then you can also do the measurements of the entangled photon fields. Okay. So that's a different topic, that how to realize different quantum processes in quantum optics. And it's also a very interesting topic, but so the point here is that we can realize, in principle, we can realize any quantum states, measurements, unitaries, and entangled states using quantum optics, and then we can send those photons from one place to another, and like realize some quantum communication products. So. Yeah. Okay, and these are the basic mathematical descriptions of the processes. Okay, so what is the communication task that we are going to discuss today? So let's say there are two parties. So one is Alice, the sender, and another is Bob, right? The receiver. Okay, and in each run of the task, so Alex gets an input. Right, and these are classical inputs. Okay. So yeah, so and that input variable is defined by x, denoted by x, right? So so each round of the task, Alex gets an input. Okay, so there is a set of inputs. Let's say 1, 2, 3, 4, 5. Okay, whatever. And in each round of the task, Alex gets one input randomly, and then Alex sends some system to Bob. Okay. It could be a classical system. If it is a classical communication, a classical system. If it's a quantum communication, it could be a quantum systems. And then Bob gets another input, again from a set of inputs randomly, and that is denoted by Y. And depending on this input Y and the message that he gets from Alice, he provides an outcome Z. And that Z is supposed to be equals to a function. Okay, so this function is given beforehand, right? So they actually have to compute this function of x and y. So they have to compute this function. This is a function of their inputs. And if Bob's answer is correct, then in that particular run of the task, I mean, they win. Alice and Bob, they actually successfully gives the correct output or computes the correct function. And this is done for many times. So like this is done for, let's say, 10,000 times. And we can try to see that what is the probability that Alice and Bob can successfully compute this function, right? Okay. So yeah, so as I said, we can from this experiment, what we get is this probabilities, that what is the output of getting Z given this input variable x and y, right? And if we run this experiment, run this task like many times, and then we can define a success metric of this communication task, which is that this z, what is the probability that this z is equals to the given function x y. So it's a correct answer given the inputs, and then you have to take the sum over all possible inputs, and we can also add a number, so a weightage for different inputs. So this is some real number, which is some weightage that you can think of. That for this particular input, the weightage is it's a 1. For some other inputs, the weightage is 2. Okay. This is a little bit more general linear function of this probabilities. That is, so this quantity actually captures the fact that what is the how good Alice and Bob can guess this function. Now, as I said, the entire this communication task, the important thing is that the dimension of the communicated system is bounded by some value d. Okay, so if it is a classical system, and if it's a quantum system, the dimension of the system has to be cannot be greater than d. So that's the constraint of this task, right? So we'll see an example and it will be more clear. So that's the constraint of the task, and then this is the success metric of the task. So this task is, as you can see, that this task is defined in terms of the classical inputs and outputs. Okay, so the task has nothing to do with quantum. I mean the definition of the task, there is the inputs and outputs. These are not quantum. These are defined by the classical inputs and outputs. But you can use quantum resources in various ways to accomplish this task, right? So this is also sometimes called as communication complexity task. So, okay, or it's also known as distributed computation. So means that the inputs are distributed among the parties that are not at the same place, and they want to compute some functions of their inputs. Okay. Okay, so you can stop me anytime and ask me questions. So, okay, so as I was saying that in classical communication, there are so what Alice and Bob can do is that they can share some classical random variable lambda before that this task starts, and they can also come up with some encoding and decoding strategy. So Alice has this encoding strategy that given the lambda and the input variable x, Alice would send some message, okay, to Bob. Okay, and so that's basically the encoding strategy for Alice. And Bob gets this message and the input y, and depending on the shared random variable lambda, Bob will give an outcome z. So that's the most general thing that Alice and Bob can do in a classical communication. And this probability that we observe in this task, that the z given xy is given by this formula, that's the probability that Alice sends the message n, given that input x and lambda. This is the probability that Alice gives an output z given that message and y, right? And then you have to take sum over all possible messages, because there are d possible messages Alice can send, and there are random variables that you also have to take care of. So there is a sort. Now, since this is a linear function of the probability, then it's not difficult to prove that this sharing this random variables lambda will not be useful. Okay, and without loss of generality, you can assume that this encoding is deterministic, like so, and also this decoding is deterministic. Okay, So it's like if Alice gets an input X, then Alice would send one of the possible messages. So there are D possible messages. The aim is like 1 to D, the D possible layers, classical. Okay. So Alice will send one of the D possible messages, and Bob, depending on Y and the message that he gets, he will answer some Z. Okay. Yeah. So with the loss of generality, you can assume that this is all possible strategies that are deterministic. Okay. Now in the quantum communication, so one thing that, so there are many ways we can use the quantum resources. So one is that Alice will send, depending on the variable X, Alice will send a quantum state to some quantum state psi X, okay, to Bob. And depending on the input Y, Bob will measure certain observables. Bob will perform a measurements on these quantum states, and the outcome of the measurement will be his answer. Right. So this is the Alice's encoding strategy is described by a set of quantum states, and importantly, since the dimension of this communication channel is D, so the state should belong to the CD. It should be a D-dimensional quantum state. And then Bob's measurements is described by a set of projectors for each Y. So for each Y, Bob performs a measurement, right? So for each Y, these measurements could be different on these quantum states, and these are defined by this set of projectors. So yeah, or in general, these are defined by a set of POVM such that each of these operator is 0. This is a positive, and sum of the operator is identity for each Y. Okay, so for each measurements should satisfy the positivity or the completeness relation. And then the probability in this case would be given by the Bond rule. So for input X, Alex sends this quantum state psi X, and for this input Y, Bob measures this particular measurements given by the set of operators, and then for the particular outcome Z, the probability is given by this. So this is the quantum communication. We will call it QC, and this is what we will mostly use in this talk. But you can use other ways like entanglement assisted classical communication. So in this case, what happens is like Alice and Bob, they share an entangled state beforehand, before the task starts. And so this is my psi AB, some entangled states. And then depending, so it's an entanglement assisted classical communication. So this is a classical communication between Alice two. So depending on the input X, Alice first measures on her subsystem. So she measures, depending on the input X, she measures, performs some measurements, and she gets an outcome A, and then she sends that outcome to Bob, and depending on Bob's input Y and the message that he gets from Alice, he would perform another measurements on his side. So these are the inputs so this is the message and this is the input. And this is the measurements that he performs on his qubit. And this is the probability of getting the Z outcome. So we take sum over all possible A, which is the first. So for X, for different measurements, there are different possibilities. So the different outcomes occur, and you have to take the sum of all possible outcomes. Of course, the message, the dimension of the message is D. So A can take like D different values, the outcome of Alice's. But you can also define a little more general quantum strategy in this case. Okay, so A could be like, so the message could be some function of AX in general, but I'm not going to discuss that. And there's another way that we can use, which is like Alice and Bob, they share an entangled state, and depending on the input X, Alice performs some unitary operation, or in general, some quantum channel he applies to her subsystem. and then send her subsystem to Bob. So this is quantum entanglement as well as quantum communication. So they shared quantum entanglement and they also use quantum communication. So in this case, yeah, so depending on Alice's input, Alice would perform some unitary on her or some quantum channel on her subsystem and send it to Bob, and then Bob now has the entire system, quantum system, and depending on his input, he would perform some measurements. And the probability of getting Z given XY would be given by this. So here, this measurements is actually acting on the composite system. And this system, importantly, should belong to C, like the dimension of the subsystem should be D because the channel has a D dimension. Okay, so yeah. So now we can, so given a task, we can also define what is the best values of the classical communication. Okay, so this is you consider all possible deterministic strategy and find out what is the best possible value of the success metric S in a classical communication. That we denote by SC. So now we will see an example which will be clear. Okay. So a simple example is this, that in this task, Alice gets an input from the set. So either 1 or 2 or 3. And Bob gets an input that is either 1 or 2. And Bob needs to guess a function, okay, of this combined inputs X and Y. And what is the function? The function is given by this table, right? So if the input X and Y are 1, 1, then the value of the function is 0. If it is like 1, 2, the value of the function is 0. If it is 2, 1, it's 0. 2, 2 is 1, is 3, 1 is 1. So, okay, so the function takes two different values, 0 and 1, right? So there's possible outcomes are 0 and 1. And this is the function that Alice and Bob wants to complete, right? But the restriction is that the dimension of the communicative system is 2. That means if it is a classical channel, then Alice can send a bit in each run of the task. And for quantum channel, Alice can send a 3 bit. Okay. So if I want to find out what is the best possible classical value of the success metric of this task. So the success metric is given by this. As you can see that this is basically the sum of this 5 possible 5 inputs, right? So this is the probability of getting the correct answer 0 given that the input is 1 and 1, right? And if the input is 1 and 2, then what's the probability of getting the correct answer 0? So that's, yeah, it's a sum of all these 5 cases. And that's my success metric. Okay, so yeah. So now, if you want to find out what is the best possible values of in the classical communication, so we will have to consider all possible deterministic strategies. So let's see what are those. So as I said, so the message is a bit or a qubit. So in the classical case, it's a bit. So there are like 2 possible values that the message M can take. So one is like 0, and each column here is a encoding strategy. So one possible encoding strategy is this, that if Alice gets input 1, then she will send the bit 0. If Alice gets an input 2, she will send the message 0. And for input 3 also she will send the message 0. Okay, so for all possible inputs, she will send the message. This could be a strategy. Okay. This strategy is not very good, because as you can see that Alice is not sending any information about her inputs, because every time he's sending like 0. But this is possible. This is one of the possible strategies that Alice can take. Okay. So it's an encoding strategy. And then here there is another encoding strategy here, that for input 1, Alice would send bit 1. For input 2 and 3, she would send bit 0. Okay. So there are actually 8 possible encoding strategies. Because for each input, there are 2 possibilities. I was sending 0 and 1. And for, yeah, there are 3 possible inputs. So similarly, Bob has actually 16 different decoding strategies. So Bob gets a message M from Alice that could be either 0 and 1, and Bob's input Y is also either 1 and 2. So there are actually 4 possible inputs Bob can get. And depending on the input, Bob can output. So for example, the one possible decoding strategy for Bob is like whatever be the message and Y, C will always output Z. So that's your answer. That's Bob's answer. The value of the function is Z. That's not a very good decoding strategy, but you can take this as it's one possible decoding strategy. Okay. So yeah, so there are like 16 possible decoding strategies. For example, this one, what this means that if the message is 0 and the input is 1, then Bob will output 0. The message is 0, the input is 2, the Bob will output 0, and so on. So you can actually check, you can consider all possible decoding and encoding strategies and check what is the maximum value of the success metric. In other words, in what are the cases that Alice and Bob can win this, can perfectly compute the function. Okay. So if I consider, let's say this is the encoding strategy which Alice takes, and this is the encoding strategy decoding strategy Bob takes, then let us see what happens. Okay. So look, let us see what happens when the input is 1, 1. Okay. So when the input is 1, 1, then look, so the Alice's input is 1, so Alice sends the message 1. Okay. And Bob's input is Y. So the message is 1 and Bob's input is 1. So in this case, Bob's output is 0. Okay. And that is the correct answer, function of f(x). So in this case, Bob gives the right answer. Okay, if the input is 1. Let us see what happens if the input is 1, 2. So again, Alice sends message 1 and Bob's input is 2. So Bob's answer is 1. So this is actually wrong. Okay, because actually the answer should be 0, but Bob gives that answer. And okay, sorry. So okay, I'm actually taking, yeah, we're supposed to consider this strategy. Okay, so let us consider that strategy instead of the last one. And let us see what happens. And like this strategy. Okay, so in the first case, Alice sends 0 and Y is 1. So in this case, it's the correct answer. In the second case also, the input is 1, 2. So Alice sends message 0 and Bob's input is 2 and the output is 2. So in this case also, it's a correct answer. For in this case, 2, 1, Alice sends message 1 and Bob's input is 1. So it's like 1, 1. And in this case, Bob gives output 0 and that's also a correct answer. For 2, 2, Alice sends 1 and so the message is 1 and Bob's input is 2, so it's also a correct answer in this case. And in the last case, Alice's input is 3, so Alice sends message 1 and Bob's input is 1, so it's like 1, 1. So in this case here, and the Bob will get the output 0. So but the actual function is 1. So in this case, Bob's answer is wrong. So out of these 5 cases, Bob actually can give 4 correct answers. Okay, and you can check that if you take any possible encoding and decoding strategy, the highest that you can get is like 4 out of these 5. So in this case, SC will be at most 4. Okay, so SC will be like the maximum value in the classical communication will be actually 4. However, let us consider this quantum strategy. Again, using qubit, so 2-dimensional quantum space. So if Alice gets input 1, Alice will send, so this is basically the XZ plane of the Bloch-Stewart. So Alice's input is 1, Alice sends this quantum state 0. If Alice's state is 2, Alice's input is 2, Alice sends the class state, it's the class state. And for input 3, Alice will send this to the plots here. This is like z-axis, this is x-axis. Yeah. And Bob's measurements is basically this. So if input is 1, then Bob will measure in this basis. So this is basically a 45-degree angle with the Z axis, and Bob's input is 2, Bob will measure in this basis. Okay, and the outcome of the measurements will be his answer. So you can check that if you take this strategy, and then if you can compute using the Bond rule, the value of the success metric will be actually this quantity, which is more than 4. It's 4.4. Okay. Yeah. So as you can see, this is an example of a task where when we allow a two-dimensional system, then the quantum value of the success metric is greater than the best possible classical value of the success metric. So this is one way of saying that we have a quantum advantage in this computation task. And there is another way of saying the same thing, that let's say if we want to get the value of the success metric to be 3 by root. So I want to get the success metric to be this value. And then I can ask, what is the dimension that is required in classical communication and in quantum communication? So I can achieve this using sending a qubit. So the dimension that is required in quantum communication is 2. But in order to achieve this, we need at least a 3-dimensional quantum system, 3-dimensional classical system. And then you have to use like mode. So DC is basically the dimension that is required to achieve the value of the success metric. So, and that is greater than DQ, which is basically the dimension of the quantum system, which is needed to get some. And that is, so DC is greater than DQ. So you need more resource in classical communication. So there are two ways you can just quantify the quantum advantage. Okay. Okay, so if you have any question, you can ask me now about this. Okay, so you can ask me that is this the most simpler scenario that we can get the quantum advantage? So we can actually consider a more simple scenario where there is an input for Bob. Okay. So it's like Alice has inputs, and then Bob has to give some Z. And Z is supposed to be some function of X. You can take this is a particular case of the communication task where Bob doesn't have any input, right? So, and then you fix some dimension of the classical channel. Okay. So in this case, there's a theorem by Franklin-Weiner. It's a seminal work, and it basically says that in this case, quantum communication doesn't give any advantage. Okay. So whatever you can get by sending a d-dimensional quantum system, you can also get the same thing by sending a d-dimensional classical system. So in order to get a quantum advantage using quantum communication, you need to have some inputs. You need to have a task where Bob has some inputs. But interestingly, if you consider the entanglement assisted classical communication, even in this scenario where Bob doesn't have any input, then you can get some quantum advantage. And the simplest example is this, that Alice has 3 possible inputs, and there are 4 possible outcomes. Okay? Z takes like 4 possible values, and the dimension is again restricted by a bit or a qubit. Yeah, it's a bit. Okay. And this is, let's say, our success metric of the task. So it basically tells you that if Alice's input is 1, then, and if the output Z is 1, then that's a correct answer. So you get a +1 point. If Alice's input is 2 and the Bob's output is 2, that's also a correct answer. And similarly for 3. But if the Alice's input is 1, this will be like 2 and this will be 3. And if Bob's answer is 4, but then you get a partial value, get a partial payoff. Not 1, but half. So if you consider this sort of success metric, then you can show that the value of the success metric in classical communication is 2. And then if you have, if you consider like entanglement assisted classical communication, even dimension 2. So let's say Alice and Bob share this Bell step. And then depending on the input, Alice measures one of the measurements. So if input is 1, then Alice measures in this basis. If input is 2, then Alice measures in this basis. And if input is 3, Alice basically sends always message 1. Okay. Yeah. So if this is the measurements that Alice performs, and Alice basically sends the measurement outcome to Bob, and depending on the measurement outcome, Bob basically measures either in the sigma x or sigma z. Okay, so if the message is 0, Bob measures sigma x, and Bob doesn't give output 3 and 4. Its output is either 1 and 2. And if the message is 1 from Alice, Bob measures sigma z, and the outcome will be 3 and 4. Doesn't give out. So if you take this frequency, then you can calculate the value of the success metric is greater than 2. Okay, it's like this actual value is this, which is greater than 2. Now, yeah, so entanglement assisted classical communication gives an advantage. Now, we can also ask the same question: what happens if we have entanglement assisted quantum communication when Bob doesn't have any input? So, can you give an example where you have a quantum advantage in this sort of scenario where you use entanglement assisted quantum communication? Anyone have any? Well, yeah. So if you have read some basics of quantum information, then you should be able to say you know a task in the scenario where quantum. Yeah. So this is basically super dense coding. So like z has to be equals to x. That's the task. Alice has to. Yeah. So but yeah. So if I just restrict d to be 2, then with 1 bit of communication is not possible, right? And let's say Alice has like 2 bits, right? The task is to basically guess the end. But if they share the maximally entangled state, and then Bob performs one of the measurements, one of the unitaries on, Alice performs one of the unitaries on her subsystem, and then this can be done perfectly. So super dense coding is an example where you have a quantum advantage in this scenario. Okay, so there is actually a limitation in this scenario where Bob doesn't have any, and the limitation is this: that in order to achieve a certain value of the success metric, the classical dimension and the quantum dimension, if I take the ratio between these two, that value cannot be greater than the quantum dimension. Okay. So in other words, if Bob doesn't have an input, everything we can achieve in log d qubits, by communicating log d qubits, can also be achieved by 2 into log d classical bits. So the advantage actually is linear. So you can, whatever you can achieve by sending 10 qubits, you can actually achieve by sending 20 classical bits. So you get an advantage, but the advantage doesn't like grow with the complexity of the task. Okay. Now, but if you consider the inputs on the Bob side, then there are examples of communication tasks where the advantage actually increases exponentially with the dimension of the quantum communication. So one of the tasks is it's called the equality problem based on graphs. So yeah, just mention about the task. Then yeah. Okay, so in this task, what happens is, let's say I have a graph. Yes, this is a graph. There are vertices, and then some vertices are connected by some edges. And the task is defined from this graph. So if I give you a graph, we can define a task. What is the task? Task is that Alice gets the input from the vertices of this graph. So there are 18 actually vertices. Okay, 18 vertices. So Alice gets an input from 1 to 18, and Bob also gets an input from 1 to 18. Okay, and the function that Alice and Bob they need to compute is a very simple thing. So it's basically whether the inputs are same or the inputs are connected by some edge. Okay, so if both the inputs Alice and Bob are the same, x and y, then the correct answer would be 0. And if x and y are connected by some edge according to the graph, then the correct answer is 1. So that's the function that Alice and Bob wants to compute. So we can define sort of a success metric accordingly. It turns out that for any such graph, the minimum dimension to achieve this task perfectly, to accomplish this task perfectly, is the minimum dimension in classical communication is required is basically the chromatic number of the graph. Okay, so that's chromatic number. So in this graph, the chromatic number is basically 5. So you need actually a 5-dimensional classical message in order to achieve this task. Perfect. So all the time you will have to Bob will give the right answer. But you can achieve this task perfectly using 4-dimensional quantum system, like two qubits. That is possible because there exist 18 vectors in 4 dimensions. These are the 18 vectors, such that if you assign these vectors in one of the vertices, you can see that 2 vectors are orthogonal with each other if they are connected. So 1 and 2 in this graph are connected, and 1 and 2 are orthogonal with each other. So basically, if Alice sends psi x for this input x, Alice will send like this vector, okay, like Vx, this state. And for input y, if Bob measures this, okay, then anyway, if x and y are the same, Bob will always get this output. Okay, this output corresponds to 0. And if x is linked with some edge, I know that this vector is orthogonal to this, so Bob will always get the correct answer, that is 1. Yeah, and this sort of quantum communication is linked with the quotient-speaker contextuality. Okay, some interesting phenomena that happens in quantum theory. And in the last 2 years, I actually talked about this quotient-speaker contextuality, this QSQT. Now, the thing is that so this is true for any graph, right? Not just this particular graph. Okay? Like the chromatic number, that is the classical dimension of the system. Okay, but it's not that for any graph you will get a quantum advantage. There are some particular graphs, but you get a quantum advantage. So you can find a set of vectors such that you can realize this graph with those set of vectors, and those vectors exist in a dimension that is lower than the chromatic number. This is the case that you can get an advantage. Now the thing is that there exist graphs, okay, where the quantum relation can be achieved by some dq, some d dimension, where d is like divisible by 4, and then the chromatic number is greater than this value. So it's greater than this value. You can show that. I mean, this is you can prove that. And for those graphs, the ratio between the classical and quantum dimension would be something like this. And this quantity actually grows exponentially when you consider this dq to be like it's greater than certain value. This ratio actually grows exponentially. So, for example, if you consider like this class of graphs, then what you can achieve with sending a 15 qubits, that is the dimension of the quantum system which would be over 15, it cannot be achieved by sending 10 to the power like 66 dimensional classical message, and this is like impossible to achieve. This is like not feasible. So sort of there exists some tasks that are impossible to accomplish in classical communication, but you can achieve with the like quantum communication with let's say 15 qubits or 20 qubits. You can achieve those things. Okay, so this is an example where we have an exponential quantum advantage. It's an example. There are many other examples like a hidden matching problem and other things. Some other examples. And I do not have much time, so I will skip this part. So you can also consider this multi-party communication task. Okay, so this is a three-party generalization of the two-party task. So you can have like three parties, Alice, Bob, and Charlie, and then Charlie has to guess certain function of the inputs of their inputs, and they are connected in linear series. You can also consider some sort of some sort of communication scenario where Alice and Bob both sends a bit or a qubit to Charlie, and in this case also you can get some quantum advantage. You can have certain tasks where you have quantum advantage, and with no inputs on the Charlie side. So references are given here. Yeah. So the last part, I just want to concentrate on a little bit different type of task, which we call the communication task and a distinguishability constraint. Okay. So in this case, what happens? Again, the task is the same. Is defined by classical inputs, and this is suppose so Bob wants to compute certain function of x and y, and analysis input and Bob's include x and y, and so that's the task basically the task. But in this communication, there is no restriction about the dimension of in the communicative system. So Alice can send arbitrary dimensional systems, classical or not. However, in this communication, the constraint is on the distinguishability of this input x. So from this message that Alice sends to Bob, anyone, including Bob, cannot distinguish the input of Alice up to beyond certain value. Okay, that's basically the restriction. Okay, so it's like this. So Alice sends I input x, and then Alice sends some quantum, let's say quantum state, depending on the input x. And then from this quantum state, anyone can try to guess what is the value of x. Okay, and that's basically a distinguishability. That how from this quantum states, I will choose the best possible measurements such that I can guess what is the input x. So that's basically the distinguishability of this set of quantum states. So let's say x has n different values. So this is basically the distinguishability of the input x, okay, from this quantum communication. And that value has to be less than certain value. That's a q. That is the restriction. So Alice's input is somewhat secret, and Alice does not want to reveal her input completely to Bob or to anyone outside her lab, right? But at the same time, Alice and Bob wants to compute this function at the same time. So it's sort of, there is a trade-off between how much information Alice wants to send, and then what is the success probability of computing this function. Now, similarly, in the classical case also, the classical case, Alice will send some classical message, right? So this is some encoding strategy. And then from this message, anyone should not be able to guess the input x beyond a certain value. Okay? That's basically the expression for the distinguishability of the input in the classical communication. So I will give an example, and just before I finish it, I will just give this example. Okay, so for example, this is an hospital, and that's the sender, that's Alice. And there are 4 possible patients come to this hospital, right? So there you can categorize them by 2 factors. One is the drug that is given to those patients and the blood group of the patients. Okay, so the blood group is basically denoted by the first bit. So it could be either 0 and 1. and the second bit is the drug that is given to the patient, and that are also like two different values of there are two different drugs. So 00 means the patient's having the blood group 0 and drug 0 is given to them. Right? Similar like 0, 1, 1, 0, and 1. There are like 4 type of patients that come to the hospital. Now, every time a patient comes to this hospital, right? There's a center who wants to know either the drug that is given to that patient or the blood group of that patient. Okay, so it's random. So either this center wants to know the first bit or the second bit. Okay, that's random. Okay, so yeah. So every time the patient comes, so the center wants to know either the drug or the blood. So basically, he wants to know the first bit or the second bit of that of this information. But the hospital cannot send both the information about the blood group and the drug. Okay, if both the informations are revealed, the hospital can actually send both the bits, right? So if the patient comes, let's say the patient is in this group, right, like 0, 1. So the hospital can send 0, 1. Okay, so it has information about the blood group and the drug. But the hospital doesn't want to do that, because if anyone in this communication knows both the things, then it's basically specified a disease, and then the hospital doesn't want to reveal the disease of that patient, right? So that is basically the secret part, that Alice doesn't want to reveal both the things, right? But at the same time, Alice wants to cooperate to Bob such that Bob gets either the first bit or the 0 bit with as high probability as possible. So this is basically the success metric, that the Z should be equals to X0 if Y is 0, and if Z is equals to Y1 if Y is 1. And then you have to take all possible inputs. That is basically 2 bits. Now you can show that if we now restrict that the distinguishability of the Alice's input is bounded by some value Q, then the value of the success metric now is a function of this distinguishability, which is 1 plus, you can show that, 1 plus Q by 2. Okay. So as you can see, if Q is 1, okay, if Alice sends both the bits, so anyone can get the full information about her input, then SC is 1. Okay. So that means the maximum value of S. But if Q is less than 1, this value is less than 1. So in particular, if you set that the value of the Q is half, that no one can distinguish the value with more than half probability, then the value of SC is 3 by 4. That's the value of the success metric in the classical communication. But now if we set the value of Q to be half, then there exist quantum strategies such that the value of the success metric is more than 3/4. Okay, so this is one of the strategies. But for input 0, 0, Alice will send this quantum state. This is again like XZ plane of the block sphere. Okay. And for input 0, 1, Alice will send this state. So this is like pi by 4, right? With these 4 states, and Bob measures X and Y depending on his input Y, and Y is equal to 1 and X to 2. And the outcome of the measurements is basically around like his answer. The first bit or the second. So if this is the case, then in quantum communication, okay, considering the same distinguishing probability, Bob can have a better success of guessing the bits random. This task is sometimes known as random access problem. Yeah. So this is, you can think of a secure computation, secure distributed computation, where the input of one party is secure. Okay. Doesn't want to reveal the full information about the input, but you do not put any restrictions on the dimension of the communication system. Yeah, so this has been studied recently in a few papers, And we have also shown that here also the advantage can grow exponentially. That means the ratio between the distinguishability in classical and quantum communication to achieve the same success, same value of success metric can go very high. So this is the distinguishability required in the classical communication, and that is more than, that means that in classical communication, Alice needs to reveal much more information than the quantum communication. This is a very interesting result. Another result is that you can also define the entanglement assisted classical communication and entanglement assisted quantum communications for the task with distinguishability constraint. And in this particular case, they are all equivalent. Okay, like quantum communications and the ESCC and EAQC, right? But this was not the case in the dimension restricted communication tasks. As I showed that with no input on Bob side, we can have advantage with the in ESCC and EAQC, right? But this is not the case. And we can also show that for this task, if Bob doesn't have any input, then there is no quantum advantage. So you have a quantum advantage, the Bob needs to have certain set of inputs. Okay, so I think I will stop here, and I'll be happy to answer questions if you have any.
Yeah, thank you, Vishesh. It was a very nice, interesting talk. So more by writing things than more interesting by making it that way. I don't see any questions in the chat box. I don't have much of questions on this. Ranjit,
Ashok, I have one question.
Please.
See, Debasis, what
Yes,
is
sir.
the experimental status of this kind of communication? For example, this multi-party particularly.
Yeah, so there are certain papers where, I mean, there are some works that are in the last 1 decade or so that people have been realizing like quantum communication in like multi-party or even bi-party. But mostly, yeah, so, but there the communication is, so the dimension that they use is like 1 qubit or 2 qubits or 3 qubits. Okay, so the dimension, it's like if you increase the dimension of the communication system, then due to the noise, you don't see the quantum advantage. Okay, so yeah, but yeah, like with 1 qubit, 2 qubit, 3 qubits, like up to 7 qubits, people have realized it and showed like quantum advantage. And all those things are done using the polarization degrees of freedom of photons.
Thank you.
I have one question. So, thank you for a very interesting and informative talk. If possible, could you summarize? Your talk.
Yeah. So again, if I want to summarize it, so the communication task or quantum communication complexity task is something like this: that Alice has some inputs, Bob gets some inputs, and Bob wants to compute some function, right? And now the question is that how much classical communication is required to compute that function versus how much quantum resources is required to compute that function, right? And we see that if we use quantum resources, then we get an advantage. Like what we can achieve with the qubit cannot be achieved with the classical bit. Okay. This is one thing. Second thing is sometimes we see the advantage to be exponentially increasing. That means what can be, for example, what can be achieved by sending a 15 qubits cannot be achieved in any feasible classical communication. But that is sort of impossible to like achieve to compute those functions in classical communications. That is one important thing. And the third thing is that when you talk about quantum resources, there are three different ways we can use the quantum resources. One is like the sending quantum systems, depending on the input, and Bose measures. The second thing is that entanglement assisted classical communications. Like they share entangled states, and then Alice sends classical message to Bose. But they use entanglement. And third thing is both. They use entanglement, and then they also use the same quantum states. That's like a superdense coding type thing. Okay. So, and then we can also like consider this, although these three things may not be at the same footing, because entanglement assisted quantum communications that are even more difficult to realize than quantum communication, right? So, but we can, one can discuss, one can take, consider these resources, and these three resources are not equivalent in general. And the fourth thing that we discussed is that the task under distinguishability constraint, which means that instead of considering the dimension as the quantification of the communication, what we can do is take the secrecy of the inputs. Okay, how much distinguish, we'll be able to distinguish Alice's input. So Alice's input is secret, so it's sort of secret communication. And then at the same time, they want to communicate, they want to compute the function. In those cases also, we can see a quantum advantage, that Alice can keep her input more secret in quantum communication and able to compute the function equally as we can do in classical communication. And the classical communication, Alice needs to reveal more information about her input. So I would guess this.
Thank you. Yes.
Yeah.
Thank you.
Yes.